Hello friends, welcome to IIT-NEET Foundation Teachers Orientation session. Today we are going to discuss about Aspirants third chapter Atoms and Molecule. Not complete chapter, few important topics from this chapter we are going to discuss. In that mainly atoms and molecules, mole concept, and some chemical calculations. How they chemical, what the way they take part in chemical reactions means what the grams of reactants reacting together and what grams of product is producing, what volumes of reactants reacting together, product producing. These all we are going to discuss with some examples. In that first, we are going to discuss about the atoms. Why? Because the basic fundamental unit of matter and its existence is what? Atoms only. Atoms are the smallest tiny particles of matter generally. Atoms are the building blocks of matter. Because of if you take any kind of matter, it is made up of atoms only. But the matter is exist in different ways. This is because of what kind of atoms and in what ratios they are combining together, they determines the existence of different kind of matters. So just below we are given one flowchart. In that the classification of that existence of atoms are given. Atoms generally exist in two ways, in combination and in free state. If they exist in combination, that is again two types. If the atoms of same element combines together, it is giving rise to a molecule of element. If the atoms of different elements combining together, it gives rise to a molecule of the compound. If there is no combination of atoms, if they are individually exist, in such cases, there is no chemical bond formation, there is no force of attractions existing between the atoms. That is in the case of inert gases. Okay. Next, the symbols of atoms are given. Generally, here each and every element has its own name. They are given by the names. But the elements, when they take part in chemical reactions and while writing the chemical equations, that is quite difficult to remember with their names and to write with their names. That is why the atoms of an elements are represented by the shorthand notation, that is called symbol. So the symbol is the shorthand notation of an element's name is called its symbol. Generally, symbol of an element is represented by first letter of its name. Okay, so here while writing the shorthand notation for the name of elements, we are choosing the first capital letter from the name of an element. But here all the elements are mostly 118 elements are there. No? In that 118 elements, few elements are repeated with the same first capital letter. In such cases, we are giving importance to one more prominent letter from its name. That means prominent letter means it may be first letter, it may be second letter along with the first letter, it may be third letter, it may be fourth letter along with the first letter. That means while naming the element, which letter is more prominent in that name, that letter is considered along with the first capital letter. So this is considered when same capital letter is repeating to the element. Okay. So here given, thus a symbol can either one or two letters in English. The first letter of the symbol is always uppercase and second letter is always lowercase. This is the first rule of the symbol. Generally, it is denoted by the first capital letter from the name of an element. If the same letter is repeating, we are giving importance to one more prominent letter. That letter should be more pronunciating letter along with the first letter in that name. So that is why we are giving importance to that prominent letter. Okay. So see here examples. Aluminium. Aluminium is what? Al. In that more prominent letter along with A is what? Aluminium. L. So Al. Carbon. C. Single letter it is carbon. Okay. Already C is given to the carbon. Now you come to chromium. Here already carbon is given to the C is given to the carbon. Then again, if you give C to the chromium, it will be confusion. Confusion. So that is why, along with the C, we are giving importance to one more prominent letter from from that name chromium. That is what R, Cr, chlorine, Cl. C is repeating. So we are giving importance to one more prominent letter. That is what in chlorine. What is the prominent second letter? C, chlorine. L is prominent letter. So we are giving importance to L, Cl, beryllium. Along with the B, we are giving importance to E, beryllium. And next, some unusual symbols. So, few elements are given by the names from Latin language. They are called Latin names of the elements. Here, antimony, copper, gold, iron, lead, mercury. These all are what elements and their English names. Latin names are strontium, cuprum, aurum. So while giving the symbols to these elements, we are selecting from the Latin name. Same. Here's strontium. S already S is given to the sulfur. So while repeating S, we are giving importance to one more letter B, SB. Carbon, C already given. So we are giving importance to one more prominent letter, that is what? U, Cu. Argon, Arum, Au. Fluorine, F icham already one. Okay, fluorine means F. Here F is repeated now. One more prominent letter, for that we are giving importance, that is what? E, ferrum. So in this way, we are writing the symbols of the elements. Next, atomic mass. So, atomic mass is generally compared with the 1/12th part of C12 isotope. So, how many times the atom of an element, the mass of an element is, how many times it is to, how many times it is more than the 1/12th mass of C12 isotope, that is called atomic mass of the element. For example, if you take oxygen, oxygen atomic mass we are considered as 16. 16. That means oxygen atom is 16 times greater than the 1/12th part of C12 isotope. So what is 1/12th part? You need to take C12 isotope. Generally, carbon is existed in the form of three types of isotopes: C12, C13, C14. If you consider C12 isotope, just you make it has the 12 parts. That each part is nothing but 1/12th part of C12 isotope. That 1/12th part is of C12 isotope is equal to 1 AMU, 1 atomic mass unit. That is, if you are expressing in grams, 1.66 into 10 to the power of minus 24 grams. This value is equal to reciprocal of Avogadro number. So 1 AMU is equal to 1.66 into 10 to the power of minus 24 grams. This is equal to reciprocal of Avogadro number. So this is what AMU. Now you consider any atom and its mass, how many times it is heavier than this 1/12th part of the C12 isotope. That is its atomic mass. Okay. Now atomic mass is also expressed in unified scale. The unit is called unified masses, denoted by capital U. Now here definition of atomic mass is given. The atomic mass of an element is defined as the average mass of all the isotopes of the element as compared to the 1/12th mass of the C12 isotope. Simple. C12 isotope we are divided into 12 parts. That one part is equal to 1 AMU. Now any atom and its mass, if you are going to consider, how many times it is heavier than this C12, 12th part of C12 isotope. That is called its atomic mass. Okay. And next, Atomic mass unit. Already I given definition to this. Atomic mass unit is nothing but 1/12th part of the atomic mass of C12 isotope, that is called atomic mass unit, AMU. The AMU is equal to the numerical value of AMU is 1.66 into 10 to the power of minus 24 grams. So here one atomic mass unit values, numerical values are given. For example, mass of C12 isotope is 12 AMUs. You know, 1 AMU is 1.66 into 10 to the power of minus 24 grams, means 12 AMU is how much? So 12 into 1.66 into 10 to the power of minus 24 grams. This is what mass of C12 isotope. And next, here examples are given. The atomic mass of some atoms. Hydrogen atomic mass is 1.0078 AMU, and oxygen is 16 AMU. Carbon atomic mass is 12 AMU. This is also expressed in grams, that is called gram atomic mass. If the atomic mass is expressing in grams, that is called gram atomic mass. Instead of AMU, we are writing with the G, means grams. Hydrogen 1 gram, oxygen 16 grams, carbon 12 grams, like that. And next, molecule. So we know atom is what? A smallest, then smaller unit of matter. That is what atom, and it is denoted by the symbols. The symbols are selected from the English names, or for few elements it is from the Latin names. Single letter we are considering. If same letter is repeating, we are giving importance to one more prominent letter. After that, atomic mass unit, everything is we discussed. Now molecules. Molecule means the smallest particle of substance with independent existence is called molecule. Atoms may not exist independently, but molecules compulsory exist independently. Why? Because just now we discussed atoms are exist in combination, atoms are exist in free state. That means may or may not they are independently exist, but molecules always independently exist. Okay, a group of atoms combining together, giving rise to a small particle. It will carries all characteristic properties of that matter. It is independently exist. That is called what? Molecule. So your molecules are again categorized into two types of molecules: homoatomic molecules and heteroatomic molecules. Homoatomic molecules means molecule of an element, means they that molecules will be contains only one kind of atoms. Molecule of element, what is the meaning of that? The atoms of same element combining together, it is giving rise to a molecule of an element. Molecule of an element is nothing but homoatomic molecules. These homoatomic molecules are again categorized into monoatomic, diatomic, triatomic, polyatomic, depends on the atomicity. So what is meant by atomicity? Atomicity means the number of atoms are combined together and giving rise to a molecule, that is called molecule of an element, that is called what? Atomicity. Means what number of atoms are combining together to form a molecule of an element. It is called atomicity. So atomicity of element is again depending on the characteristics of the elements. Okay, but here depends on atomicity. The molecules are again categorized into monatomic molecules, diatomic molecules, triatomic, polyatomic molecules. Monatomic molecules means what? A single atom, the atoms are not combining together. Atoms are existing freely. They are not at all showing any interest to combine with the adjacent atoms of same element. They are inert in nature. That kind of molecules are called monoatomic molecules. So, so simple, monoatomic molecule means the smallest particle which is with independent existence. Here That smallest part, if you take inert gas argon, in that argon, air is what? Atom only, but it is independently exist inside that argon sample. That is why it is called molecule. But that molecule is contains only one atom, no? So therefore it is monoatomic molecule. So example, inert gases. And diatomic molecule means two atoms are present in a molecule. It means two atoms combining together and forms the molecule. Such kind of molecules are called diatomic molecules. Example, N2. N2 means two atoms of nitrogen combining together and independently exist as a nitrogen molecule. O2 means two atoms of oxygen combining together and giving rise to a O2 molecule. Two atoms of hydrogen combining together and giving rise to a H2 molecule. So, in this triatomic means what? Three atoms of an element combining together and giving rise to a molecule, that is a triatomic molecule. Four tetraatomic, like that. So, poly means number of. If three are more than three, more than three, more than four, like that, if you take the number of atoms inside the molecule, that kind of molecules are called polyatomic molecules. Example, phosphorus, sulfur. Sulfur contains 8 atoms in its molecule, like that. Okay. Now we come to second category of molecules. Molecules of a compound. Molecules of a compound means what? Atoms of different elements combining together and giving rise to a molecule. That molecule is called molecule of a compound. It is called heteroatomic molecule. Molecules of a compound is also called heteroatomic molecules. Why they consider heteroatomic molecules? Because of the atoms of different elements combining together. Atoms of different elements combining together and giving rise to a molecule. Hetero means different. Atomic means atoms. Different atoms of different elements combining together and results the formation of molecule. Therefore, they are called heteroatomic molecules. Simply we can say molecules of compounds. Example, Cl, H2SO4. H2SO4. In this H2SO4, two atoms of hydrogen, one atom of sulfur, four atoms of oxygen combining together and giving rise to a molecule of sulfuric acid. So this is the heteroatomic molecule, HCl, one atom of hydrogen, one atom of chlorine. And it gives rise to HCl molecule. One atom of sulfur, three atoms of oxygen gives rise to a sulfur trioxide molecule. Two atoms of hydrogen, one atom of oxygen gives rise to a hydrogen monoxide molecule, nothing but water molecule. So in this way, molecules are existed with the atoms of same element and with the atoms of different elements. So therefore they categorized as a heteroatomic molecules and homoatomic molecules. Now, molecular mass. Within the name only we are getting its meaning. Molecular mass means mass of the molecule. Mass of the molecule. Then how we determine the mass of the molecule? Simple. Molecule contains the number of atoms. Okay, no? So if we calculate the total mass of the atom, that is gives rise to molecular mass. Whatever the number of atoms present within a molecule, the total number of atoms mass is nothing but molecular mass. So therefore it is defined as the sum of the masses of all atoms present in a molecule is called its molecular mass. So whatever the number of atoms are there, we are taking the total mass of the atoms within that molecule, that is gives rise to a molecular mass. For example, if you take CO2, in CO2, one carbon atom, two oxygen atoms are present. So one carbon, two oxygens. One carbon atomic mass is how much? 12. So 1 into 12. Two oxygen atoms, each oxygen atom carrying the atomic mass 16. So 2 into 16. Sum of the atomic masses is nothing but molecular mass. So we need to take number of atoms of each element into its atomic mass. So 2 into 16. So 12 plus 32. Total 45 unified masses. 44 unified masses. Means 44 grams. Okay, gram atomic mass is expressed in grams, no? 44 grams. H2O. In H2O, hydrogen and oxygen combines in the ratio of 2 is to 1. So, hydrogens 2 are there now. So, 2 into 1. 2 ones are 2. Oxygen 1. 1 oxygen atomic mass is 16. So, 1 into 16. 16. 2 plus 16, 18 unified masses, 18 grams. Similarly, calcium carbonate, CaCO3. They combines in the ratio of 1 is to 1 is to 3. So 1 into 40, 1 into 12, 3 into 60. Total 40 plus 12 plus 48, 100 grams. Next, this is what molecular mass. Now we come to formula unit. Before going to the formula mass, we are coming to the formula unit. So what is meant by formula unit? So generally, formulas are two ways we express for ionic compounds and normal covalent compounds. Molecular formula means the symbolic representation of atoms of an elements present within a molecule, that is called what? Molecular formula. Formula unit means generally in case of ionic compounds, once you observe this crystal lattice, if you come to the ionic compounds, in ionic compounds, you know, positive charged and negative charged ions are combined together and giving rise to ionic compound, we know that. So in ionic compounds, each positive charged cation from all the directions combines with the negative charged anions. So in ionic compound, each ion is surrounded with the opposite charged ions. Opposite charged ions. That means ionic bond is non-directional bond. It is not formed in one direction. Why? Because generally while writing the cations or anions, we are writing the charge at the top right like this. So Na plus 1. What is the meaning of this? This positive charge is accumulated throughout the sodium, throughout the atom of sodium, not at the right top of the sodium atom. Okay? So this positive we are writing at the top right. That means it is not accumulate this charge at the right top only. This charge is accumulated throughout the sodium atom. So that means this corner at the right, left bottom corner, left top corner, any point of sodium if you are consider, it is existing with what charge? Positive charge. That means completely throughout the mass of atom it is existed with the positive charge. If you consider Cl minus, generally simply we are writing Cl minus 1 like this. Meaning is this negative charge is accumulated throughout the chlorine atom, not at the one corner. That means if you take positive charged or negative charged ions, the charge is accumulated throughout the mass of that negative ion and positive ion. So that means from all the directions it is ready to attract opposite charged ion. So see this structure, lattice structure. In this sodium is from all the directions it is attracting the negative charged chlorine atoms. Chlorine atom from all the directions it is attracting the positive charged sodium atom. So here see positive charged sodium, here positive charged sodium, here positive charged sodium, here positive charged sodium. Why? Because this chlorine is, throughout the mass of chlorine is carrying what charge? Negative charge. It is ready to attract so opposite charged sodium atoms from all the directions. In such cases, they give rise to a structure that is called crystal lattice. In this crystal lattice is generally for the ionic compound. In this crystal lattice, each ion is surrounded by the opposite charged ions. In such cases, this is unlimited structure formation takes place. Sodium chloride again here, see here, this is uncontrolled structure. Here again sodium, here again chlorine, and here again sodium, here again chlorine, and this is what sodium. See, continuously we can write this structure. It is endless. Then how can you take the molecular formula? It is a not independent particle. So that is why we are taking the simplest ratio by which the positive charged and negative charged ions are combined. That is called formula unit. The simplest simplest ratio the positive charged and negative charged ions combines together in a crystal lattice, that is called formula unit. So in case of ionic compounds, we need to consider the formula units, not molecular formulas. Okay? If you take H2O, H2O meaning is one H2O is independent particle, independent molecule. In water, H2O is independent molecule. But in case of sodium chloride independent NaCls are not there. They are combined like a crystal in this crystal lattice. Okay, so that is why what the simple ratio the opposite charge ions are combined together and giving rise to a unit, that is called formula unit. So your definition is given: the symbolic representation of smallest unit of non-molecular substance. So it is not molecule. Molecule meaning is what? The independent existence of a particle in a matter is called molecule. Here any part is independently existing in this crystal lattice? No. So therefore, the symbolic representation of the smallest unit of non-molecular substance means ionic compound is called formula unit. In that formula unit, whatever the ions are there, its mass is considered as a formula unit mass. For example, formula unit of sodium chloride is NaCl. Okay, its formula unit mass is how much? Total how many sodium chlorides are sodium and chlorine ions are considered in this? One sodium, one chlorine. So sodium mass is 23 and chlorine mass is 35.5. Total 58.5 unified masses, 58.5 grams. Okay. Now we come to the ion. So ion means, ion is simply we can say charged species is called ion. Charged species, it is either positive or negative. Some charge it is carrying, that is called ion. So ion is an atom or group of atoms that has an electric charge. It is either a positive charge or a negative charge. But if it is carrying the charge, that is called ion. So ions, how the ions formation takes place, we see that. Ions are generally two types, positive charged ions and negative charged ions. Positive charged ions are called cations and negative charged ions are called anions. So how the ions formation takes place? Just you take this is the atom, neutral atom. When atoms are losing the electrons, they form the cations. Why? Generally we know in neutral atom the number of positive charged protons are equal to the number of negative charged electrons. The charge of proton is equal to charge of electron but opposite charges. Proton is carrying the positive charge, electron is carrying the negative charge. Both number of protons are equal to number of electrons in the neutral atom. At the same time, charge of protons are equal to charge of electrons. So if you take neutral atom, number of positive charges are equal to number of negative charges. That is why atom is neutral. If negative charge carrying electrons are removed from the atom, then what happened? The positive charge density is increased in the atom. Increased means it is more than the negative charge. Increasing means not extra charge is coming in that species. Whatever the charges are there, negative and positive is negative and positive is equal. Okay, that is neutral. If negative charged particle, if you are taken out, automatically positive charge density is more in that species, resultant species. That is called, that means what? It is carrying the positive charge on it. That is called positive charged ion, nothing but electropositive ion, nothing but cation. So that means the neutral atom, whenever it is losing the electrons, it is acquired by the positive charge on it, electrically positive charge on it. That is called electropositive ion, nothing but cation. And If the neutral atom is gaining the electrons, the resultant species is acquire the negative charge on it. That is called anion. Simple. Number of negative charged particles and positive charged particles with their charges is equal and it is neutral. If you are adding negative charged species to that neutral atom, the negative charge density is more on that ion, that atom. Then that is carrying what negative charge, that excess of charge, whatever it is aqueous, that is carrying by that species, that is called negative charged ion, nothing but electronegative ion called anion. Now here, cations and anions are carrying the different amount of charge on them. Plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. This is again depends on the what number of electrons they are losing and gaining. So depends on the number of electrons losing and gaining. The electropositive character, the number of the number of positive charges and number of negative charges carrying by them is determines. We'll see for the cations. If the positive charge carrying species is there, that is called cation. Now, if that ion existence formation takes place by the loss of one electron, that is called monovalent electropositive ions. That means what? A neutral atom of an element, by losing an electron, one electron, they are acquires one positive charge on them. Such cations are called monovalent electropositive ions. By losing one electron, they acquire a positive charge on them, electrically positive charge on them. So therefore, they are called monovalent electropositive ions. Example: rubidium, okay, Rb plus 1, Cu, Q plus ion, and H plus, Na plus, K plus. These all ions are formed by losing one electron. Okay, they are monovalent electropositive ions. Divalent electropositive ions means the neutral atom is losing two electrons. By losing two electrons, they acquire two positive charges on them. Such a kind of positive, two divalent electrons, such kind of positive charged ions are called divalent electropositive ions. That means they are carrying plus 2 on them. Okay, positive charges on them. Next, trivalent. If it lost 3 electrons, trivalent electropositive ions formation takes place. Example: CO3 plus stibm3 plus CSB3 plus Al3 plus Fe3 plus, like that. And next, come to the anions. If the neutral atom is gaining the electrons, the resultant species is acquired the negative charge on it, that is called anion, otherwise electronegative ion. Electrically negative charge it is carrying. That is why it is called electronegative ion. So again these electronegative ions are existed as monovalent electronegative ion, divalent, trivalent electronegative ions, depends on the what number of electrons they are gaining. If a single electron is gained by it, neutral atom, monovalent electronegative ions formation takes place. That means it is carrying one excess of negative charge on it. Okay. If two electrons gains, that is divalent electronegative ion. That means it is carrying two electrically negative charges on it. Trivalent means by gaining 3 electrons, trivalent electronegative ion. So in this way, depends on the number of electrons losing and gaining. They are forming monovalent, divalent, trivalent positive ions and negative ions. Okay. So this mono, divalent we are saying because of depends on the number of electrons losing, gaining, sharing, only the valency of the atoms of an element determines. That is why they consider as monovalent, divalent, trivalent, negative ions and positive ions. Okay. And now come to the valency. Valency simply we can define, just now we say the combining capacity of an element is called valency. That means with same element, atom of same element or atom of different element, with what the way they combines. That combining capacity is called its valency. So the valency of an element is explained with respect to hydrogen, chlorine and oxygen. The combining capacity of each and every element is explained with respect to hydrogen, chlorine and oxygen. Why? Because all the elements do not possess same valency. Their combining capacities are different. So their combining capacities are explained by comparing with the hydrogen, chlorine and oxygen. So these are considered as the references. So for example, with respect to hydrogen, if we see these examples, you understand what is valency with respect to hydrogen and how we define the valency of an element, how we find the valency of an elements with respect to hydrogen and oxygen. Okay, see here. Generally, hydrogen combining capacity is 1. Everyone know that. Number of hydrogen valency 1. You remember that. Number of hydrogen atoms. Number of hydrogen atoms combines with an atom of an element determines its valency. For example, if you take sodium, sodium is sodium is one of the element. One atom of sodium is combining with one atom of hydrogen. So that means what here? Sodium atom is combining with one atom of an hydrogen. So therefore sodium valency is how much? 1. Here definition what I said in definition, what number of hydrogen atoms are combining with one atom of an element, it is determines that element valency. So here sodium is atom of an element, it is able to combine with one atom of hydrogen. So therefore sodium valency is 1. And next, hydrogen chloride molecule. In this, chlorine is combines with one atom of an hydrogen. So chlorine valency is 1. Simple. What number of hydrogens combines with the atom of particular element, it determines the valency of the particular element. NH3. In NH3, nitrogen atom is combines with 3 atoms of hydrogen. So therefore valency of nitrogen is how much? 3. So combining capacity of an element is explained with respect to this hydrogen. With what number of hydrogens it is combining, it is determines its valency. Okay. Now with respect to chlorine. So everyone know about the valency of chlorine. Valency of chlorine is 1. So here number of chlorine atoms are combines with one atom of an element is determines its valence. Simple, just like a hydrogen. So here what number by which chlorine atoms are combining with the atom of an element is determines its valence. Example, magnesium chloride. In magnesium chloride, each magnesium is able to combine with how many hydrogens? Sorry, how many chlorines? 2 chlorines. So therefore, magnesium valence is 2. So number of chlorines combines with the atom of an element is determines valency of that particular element. So here magnesium is combining with 2 chlorine atoms. No? So therefore magnesium valency is 2. AlCl3. In AlCl3, one aluminum is combines with 3 chlorines. Therefore aluminum valency is 3. Now with respect to oxygen. So everyone know oxygen valency. If you take oxygen valency is 2. Oxygen valency is 2. That means it is able to combining capacity of oxygen is 2. So here, based on the definition is given with respect to oxygen valence definition of an element. Twice the number of oxygen atoms combines with one atom of an element is determines its valence. That means, see, if you see the examples, we get it. Calcium combines with one atom of an oxygen. So, with what number oxygen atoms are combining with the particular element, you have to twice that number. Here, one oxygen is there, not twice this number. Twice means 2. So, why? Because one oxygen atom valence is 2 now. So what number of oxygen atoms are combining with one atom of an element? Twice that number. it is determines the valency of that particular element. So here calcium is combining with one atom of an element, one atom of an calcium. So twice the number of oxygen atoms. Here one is there now, you have to take two. So therefore calcium valency is how much? 2. Here calcium valency is 2. Now aluminium oxide. So in this see, two aluminiums combines with three oxygens. Two aluminiums combines with three oxygens. Total within the aluminium trioxide molecule, how many oxygens are there? Three oxygens. Twice this number. 3 to the 6. Double this. 3 to the 6. 6 means here two aluminiums are there. Two aluminiums combines with three oxygen atoms. 6 means here twice the number means 6. Here two aluminiums share that valency. So each aluminium, two aluminiums are there now. 6 valency is sharing both of them equally. Then each aluminium carrying valency is how much? 3. Okay, each aluminium carrying the valency 3. CO2. In CO2, two oxygen atoms combines with one carbon. So twice the number of oxygen atoms. 2 means 4. So carbon valency is 4. So in this way, with respect to hydrogen, chlorine and oxygen, we determine the valency of the elements. Now, variable valency. Variable valency means atom of an element has its own combining capacity, but few elements exhibit more than one valence. Such elements are called variable valent elements and the valency is called variable valency. So, they are exhibit more than one valency. Combining capacity of that elements is different, depends on what number of atoms are available in the surroundings and they will be take part in the bond formation, they take part in the combination with that surrounding elements, and in such cases they will be possess variable valency. Okay. Variable valency means they are exhibiting more than one valency. No? So variable that element is called variable valent element and the valence is called variable valency, higher valency and lower valency. What is the higher valency, lower valency? When atom is posing two different valencies, the more valent one is called what? Higher valency, lesser one is called lower valency. If higher and lower valencies exhibiting by a single element, that element, the end name of the element is suffixed with ik. The end name of the element is suffixed with what? Ik. And as. If lower valence is there, as. Higher valence is there, ik. So how can we recognize that, how can we show that higher valent, lower valent element, how can we name that higher valent, lower valent of the same element with the suffix of ik and as. The end of the name of an element is suffixed with the ik if in case of higher valence. End of the name of the element is suffixed with as in case of lower valence. Example, if you see the examples we can get it. Ferrous. Generally ferrum is there, iron. It is posing two different values, plus 3, plus 1. Plus 3, plus 1. Plus 3, plus 2. Plus 3, higher valence, no? Ferrum. The end of the name of an element, ferrum, is suffixed with what? Ik. That um we are removing from that, we are adding what? Ik. Ferric. If lower valence is there, ferrum, we are removing that end part and we are removing the tail part and we are adding what? Suffix as. Ferrous. Ferric, ferrous. If you take the cuprum higher valence is plus 2, lower valence is plus 1. Suffixed with what? Cupric. Cuprum, that tail part removing and adding the ik. Cupric. Here cuprous. Argentic, argentus. Mercuric, mercurous. That means what? From these names only we are finding it is lower valent or higher valent. Okay, ferric ion. Okay, means Fe3 plus ion. Ferrous ion means Fu2 plus ion. Cupric ion means Cu2 plus ion. Cuprous ion, Cu plus 1 ion, like that. Okay, so in this way, positive elements will be possess the different valencies. They are called higher valent element. They are suffixed with the ic and has. Now, molecular formula. Molecular formula means the molecule of an element is in short form notation representing, that is called what? Molecular formula. Simply symbolic representation of molecule is called its molecular formula. Simple. What kind of elements and what number of atoms of that elements are present within a molecule, they are represented by their symbols and subscript numbers. That is called what? Molecular formula. That means what? For example, molecular formula is giving rise to what information about the number of atoms of element, number of atoms of an element, and types of an element, and what type of elements are present in that molecule of compound, and what number of atoms of each element is present. That explanation is given by the molecular formula. See here, example H2O. What is the meaning of H2O? Here two kinds of information we are getting: types of elements and atoms of each element. Here types of elements are what? Oxygen and hydrogen. Oxygen and hydrogen. Two types of elements are present in this water molecule. And what number of atoms of each element is present in that also we are getting. Two atoms of hydrogen, one atom of oxygen. Combining together, giving rise to what? Molecule of water. So that means what? Molecular formula is the symbolic representation of molecule of an element. Is called, molecule of an compound is called molecular formula. So this molecular formula, in this molecular formula, the atoms of an elements are represented by the symbol. What number of atoms of each element is present, that is denoted by the subscript number at the right bottom of symbol of an each element. Here two atoms of hydrogen is present now. Two atoms of hydrogen present within water molecule now. So hydrogen and subscript number is 2. One atom of oxygen present within a water molecule, one atom of oxygen. So number of atoms are denoted by the subscript number. Type of element is denoted by its symbol. It is giving rise to a molecular formula. The molecular formula is helpful to us in the chemical, stoichiometric chemical reactions, analytic chemical reactions. Means what amount of reactants are reacting together and product is producing in the reaction, and what volumes of reactants reacting together, volumes of product producing in the reaction. That all calculations are depends on these molecular formulas only. Okay, symbols and molecular formulas. Okay, with the help of the symbols of an elements and molecular formulas of the compounds only, we are writing the chemical equations, and we are doing the stoichiometric equations. Okay, and stoichiometric calculations. And next, writing the molecular formula of the compounds. Writing the chemical formula. Molecular formula is nothing but chemical formula by using the crisscross method. So in crisscross method, several steps are there. By following that steps, we are writing the molecular formula. Okay. Now we see that first step by step we will go. Write the symbols of each ion side by side. Usually the cation first and anion next. That means simply, while writing the molecular formula of the molecule, first you identify the positive charged and negative charged ions present in that, cations and negative charge, cations and anions. Positive charged cations, left hand side you are writing, and negative charged negative charged anions, right hand side. Means first we are writing cations. After that, anion. So this is the first step. Next, next step, divide the valency numbers their highest common factors. If more than one valence is there, valence numbers are there. If any suitable common factor is there, with that we need to divide the valence numbers. For example, here not there. For example, here 2 is there, here 4 is there. 2 ones are 2 twos are. Like that. Divide with the common factor, and we are getting the simplest ratios of the valency numbers. After that, in third step, we are ignoring the charges and writing only valency numbers. Here plus 1 is there, we are ignoring the plus. Here minus 2 is there, minus we are ignoring. Okay, and only we are writing the charge numbers. While writing the charge numbers, if any subscript number is there for the ions, we need to enclose that ion within a bracket. Okay, then we are interchanging the charge numbers. In next step, we are interchanging the charge numbers. Carbonate ion is carrying the charge number 2, that is changing to the sodium, and sodium ion is carrying the charge number 1, that is interchanging towards the carbonate to the either side right bottom to the symbol of an elements and ions. Now 2 is interchanged to the sodium at the right bottom Na2, and 1 is interchanged to the CO3 at the right bottom as CO3 minus 1. Sorry, CO3 1. If 1 is there, we are getting 1, no need to write that 1. And next, if any constituent, already we discussed this, if any constituent receives the number 1, ignore while writing the formula. And next, if a constituent, already this also I said, if a constituent has more than one atom enclosed within a bracket, already I said this, that means that subscript number, which one is carrying the subscript number more than 1, you need to close within a bracket, enclose within a bracket. If it carries 2 or more than 2. Okay. Hence the formula of the sodium carbonate is Na2CO3. See here. Already we interchanged that numbers. Finally we got Na2CO3. And now mole concept. Generally the mole concept is playing a prominent role in the chemical calculations. With the help of this mole concept, the mass of the substances and volume of the substances, or number of molecules of the substances and atoms of the substances take part in chemical reactions and produced in the chemical reactions, we are calculating in simple way with the help of mole concept. So mole means what? Mole means it is defined as the amount of substance which contains the same number of chemical entities as number of atoms, exactly 12 grams of C12 isotope. C12 isotope means 1 mole means the number of chemical entities present in 12 grams of C12 isotope, that is equal to 1 mole. That is equal to 1 mole. So 1 mole definition is given to the mole. The amount of substance containing Avogadro number of chemical entities is also called 1 mole. So what is the meaning of this? If you take 12 grams of C12 isotope, it contains Avogadro number of carbon atoms. Avogadro number of carbon atoms. Avogadro number of carbon atoms means how much? If you take 12 grams of C12 isotope, C12 isotope means carbon isotope, it contains 6.022 into 10 to the power of 23 carbon atoms. So this is a fixed number. This number is called Avogadro number. So any If you take any component, gram atom of element, gram molecule of the component, it contains same chemical entities as C12 isotope contains. C12 isotope contains how many chemical entities? How many units of carbon atoms? 6.022 into 10 to the power of 23 carbon atoms. If you take any chemical entity, 1 gram atom, 1 gram molecule of any chemical entity, chemical component, it contains that particular number of atoms of molecules of ions. That is called what? 1 mole of substance. So the amount of substance is expressed in moles. 1 mole is how much? The same number of chemical entities present as number of chemical entities present in C12 isotope. That number is how much? Avogadro number. What is that number? 6.022 into 10 to the power of 23. That is denoted by Na. Generally, mole is the SI unit of chemical quantity. Now, here one table is given based on mole concept. If we see this table, complete information we will get about the maximum information we will get about the mole concept. See here, 1 gram atom of an element, if you take 1 gram atom of an element, 1 gram atom of an element, it is called gram atomic weight. Gram atomic weight is expressing in grams. No? So 1 gram atom of an element is called gram atomic weight. Gram atomic weight of any element is nothing but it consists 1 mole of atoms. 1 mole of atoms of that particular element. So 1 mole of atoms of that particular element is how much? Already in the definition we defined. 1 mole of atoms of an element contains, 1 mole contains Avogadro number of atoms. This Avogadro number, how we determine this Avogadro number? By taking the number of chemical entities, chemical units in the C12 isotope. This C12 isotope contains how much? This fixed number of atoms. That is only considered as Avogadro number. So, any 1 gram atom of an element you are considering, it is nothing but gram atomic weight. Gram atomic weight of that element contains 1 mole of atoms of that element. 1 mole of atoms of element is how much? Avogadro number of atoms. So this Avogadro number of atoms occupies 22.4 liters of volume at standard temperature and pressure conditions. That is how much? 22.4 liter. That volume is called molar volume. Simply, 1 mole of substance at STP occupies 22.4 liters. That volume is called molar volume. The volume occupied by a mole of gas, a mole of substance at standard temperature and pressure is called molar volume. That is 22.4 liters. Now example. We'll consider one example. 1 gram atom of nitrogen, if you take 1 gram atom of nitrogen, it is gram atomic weight of nitrogen is how much? 14 grams. So 1 gram atoms of nitrogen is 14 grams of nitrogen. 14 grams of nitrogen atoms. 14 grams of nitrogen atoms is equal to how much? Here already we discussed now. 14 gram atomic weight of atoms of an element is equal to 1 mole of atoms. So here 14 grams of nitrogen atoms are equal to 1 mole of nitrogen atoms. 1 mole of nitrogen atoms. 1 mole of nitrogen atoms. So 1 mole of nitrogen atoms contains how many atoms? Avogadro number of atoms, that is about 6.022 into 10 to the power of 23 nitrogen atoms. That means if you take 1 gram atom of nitrogen, it contains 6.022 into 10 to the power of 23 nitrogen atoms. So this number of nitrogen atoms occupies 22.4 liters at STP conditions. Okay, at standard temperature pressure conditions. 6.022 into 10 to the power of 23 nitrogen atoms occupies how much? 22.4 liters of volume. So therefore molar volume of nitrogen atoms, 1 mole of nitrogen atoms is how much? 22.4 liters. Simple. 1 gram atoms is equal to gram atomic weight. Gram atomic weight of the element is equal to 1 mole of atoms. It contains 1 mole of atoms. 1 mole of atoms is Avogadro number of atoms. It occupies a volume at a standard temperature and pressure, that is called molar volume. It is always 22.4 liters. Simply. Here about gram atom we discuss now. Now gram molecule. If you take 1 gram molecule, it is equal to gram molecular weight. It is nothing but gram molecular weight. 1 gram molecule is equal to gram molecular weight. Gram molecular weight of the substance is equal to 1 mole of molecules. 1 gram molecular weight of the substance is equal to what? 1 mole of molecules. Means 1 mole of molecules contains how many molecules? Avogadro number of molecules. That is about 6.02 into 10 to the power of 23 molecules. These many 1 mole of molecules are occupies 22.4 liters of volume at standard temperature and pressure conditions. That is called molar volume of a gas and substance. Okay. So this is what for 1 gram molecule. Example, their nitrogen atom we consider here 1 gram molecule of nitrogen we are considering. N2 is a molecule. So 1 gram molecule of nitrogen is 28 grams of nitrogen. Why? Because gram molecular weight of nitrogen is how much? 28 grams. So 28 grams of nitrogen molecules. This 28 grams of nitrogen molecule occupies 28 grams of nitrogen molecules contains how many molecules? 1 mole of molecules. 1 mole of molecules is nothing but Avogadro number of molecules. 6.022 into 10 to the power of 23 nitrogen molecules. They occupies 22.4 liters of volume at STP. So, from these 4 lines we are getting a lot of information, and we can do a maximum number of numerical problems based on these 4 lines information. For example, see here, number of moles of atoms, we know weight of substance by gram atomic weight. Here number of moles of atoms are given. In case of atoms, we need to take here gram atomic weight. Number of moles of molecules, if you consider here, gram molecular weight we need to take. So number of moles of atoms is denoted by number of moles denoted by n, small n. So number of moles n is equal to weight of the substance. Means weight of the substance means what amount of that sample of an element is considered. That is nothing but what weight of sample of an element considered. That is nothing but what weight of the substance. Weight of substance by gram atomic weight. Okay, so this is what number of moles. So number of moles of sodium atoms in 92 grams of its sample. See here, example problem. Number of moles of sodium present in number of moles of sodium atom present in 92 grams of its sample. So we need to find out that number of moles of sodium is equal to weight by gram atomic weight. Weight of the sample is how much? 92 grams. So 92 by 23. So number of moles are 4. So 92 grams of sodium if you take, it contains how many moles? It is equal to 4 moles. That means 4 moles of sodium chloride is 92 grams. Okay, next. Number of molecules formula. Number of moles of molecules. Just now I said if you take molecules, we need to take here gram molecular weight. Okay, number of moles of molecule if we are considered gram molecular weight. Number of moles of molecules is equal to weight of substance by gram molecular weight. Example problem. Number of moles in 880 grams of CO2. You need to see here while doing the problems. In problems, what molecule is given? Atom is given. We need to identify that first. Here molecule CO2 is a molecule. So we need to find out a gram molecular weight. Sometimes they will give. If they won't give, sum of the atomic weights gives rise to what? Molecular weight, gram molecular weight. Okay. So weight of the sample already here given. So number of moles of CO2 is equal to 880 by weight by gram molecular weight is 44. So 880 by 44 is how much? 20. So 880 grams of carbon dioxide is equal to 20 moles of CO2. Okay, 20 moles of CO2. Now, Some more example problems on based on mole concept. Number of atoms present in 23 grams of sodium. 23 grams of sodium. See here, we need to identify there is it is atoms or molecules. We need to identify first that. So number of atoms in 23 grams of sodium. We need to find out the number of atoms. Formula is what? Weight by gram molecular gram atomic weight into Avogadro number. Why? Because you know 1 mole contains Avogadro number of atoms. Already in the table we discussed that. 1 mole contains Avogadro number. That number is a fixed number, that is about 6.022 into 10 to the power of 23. 1 mole contains that much. So here weight is given. Weight of the element is given. Gram atomic weight already we know. Gram atomic weight is what? Sodium is how much? 23. So weight and gram atomic weights we know. With the help of these two quantities we need to find out the moles. 1 mole contains how many number of atoms we know. If we find out the number of moles into Avogadro number gives rise to what? Number of atoms present within the sample. So therefore first we need to find out the number of moles. For that, number of moles formula is what? Weight by gram atomic weight. So weight by gram atomic weight. It giving rise to what? Number of moles. N. N value it is giving. So number of moles. Each mole is contains Avogadro number of particles. No? So therefore, what number of moles you are getting, that number of moles you are multiplying with what? Avogadro number. So it is giving rise to what? Number of molecules. So number of moles to weight by gram atomic weight. This is giving rise to number of moles into Avogadro number. Okay, Avogadro number. So this is what 6.022 into 10 to the 6.0. 23 ones are we are getting 1 only. So therefore 6.022 into 10 to the power of 23 sodium atoms. That means if you are taking 23 grams of sodium, it contains 6.022 into 10 to the power of 23 sodium atoms. Now one more example. Number of moles in 60 grams of sodium hydroxide. 60 grams of sodium hydroxide. So here also weight is given, sample weight is given, and molecular formula also given. With the help of this molecular formula, we need to find out gram molecular weight. Sorry, here gram, not atomic weight. This is gram molecular weight. So weight by gram molecular weight. Sodium hydroxide is a molecule. Here 60 grams. Sample weight is 60 grams. With the help of NaOH formula, we need to find out gram molecular weight. So N, number of moles formula, we know. N is equal to what? W by gram molecular weight. So 60 by 40. 1.5 moles. 1.5 moles. 1.5 moles. So what is the meaning of that? If you are consider, okay, so now number of atoms in 6.4 grams of sulfur. 6.4 grams of sulfur is equal to number of atoms. Formula we know. Weight by gram atomic weight. It gives rise to a number of moles. Number of moles into Avogadro number gives rise to number of atoms. So therefore number of atoms is equal to W by GAW into Na, means weight of the substance by sample by gram atomic weight into Avogadro number. So we could 6.4 by 32. Weight of the sample is 6.4. Weight of the sample is 6.4 and gram atomic weight 32. 6.4 by 32. Atomic weight of sulfur is 32, means 6.4 by 32 into, it gives rise to, this value gives rise to number of moles. This value gives rise to number of moles. So number of moles into Avogadro number gives rise to number of atoms. So 6.4 by 32 into 6.022 is gives rise to 38.54 by 32 into 10 to the power of 23. Its value is 1.2 into 10 to the power of 23 sulfur atoms. That means if you take 6.4 grams of sample of sulfur, it contains 1.2 into 10 to the power of 23 sulfur atoms. Now, Avogadro's law. Avogadro's law, this is very important law. 1 mole of any gas at STP always occupies a volume of 22.4 liters. That means any gas, 1 mole of any gas, if you consider hydrogen, oxygen, nitrogen, 1 mole of hydrogen gas, 1 mole of nitrogen gas, 1 mole of oxygen gas. It's the same similar conditions of temperature and pressure. It's under temperature and pressure. These three gases contains same number of molecules in the 22.4 liters. That means equal volumes of the three gases contains equal number of particles at STP conditions. 22.4 liters of oxygen, 22.4 liters of nitrogen, 22.4 liters of hydrogen, you considered in 3 cylinders. These 3 samples contain same number of molecules. Hydrogen molecules, 6 points, Avogadro number of molecules. Already in the table we discussed that 1 mole of gas, any gas contains at STP conditions contains Avogadro, occupies 22.4 liters of volume, it contains Avogadro number of molecules. So based on that, Avogadro law is defined. What is that? 1 mole of any gas at STP always occupies a volume of 22.4 liters. So you consider different sample of gases. At STP conditions, they occupies 22.4 liters of volume. They contains equal number of particles, that is Avogadro number of particles. See here, 1 mole of CO2 is there, 1 mole of ammonia. Both are different gases. At STP conditions, both are occupies same volumes, 22.4 liters, 22.4 liters. And next, volume of 3 moles of hydrogen sulfide at STP. See here, based on the table only we can do this. 1 mole is occupies how much? 22.4 liters. But here in question is asking about 3 moles. 1 mole occupies 22.4 liters. 3 moles occupies how much? Question mark. So X is equal to 3 into 10 to 22.4 liters by 1. It gives rise to 67.21 liters. That means if you consider 3 moles of hydrogen sulfide gas at STP, it occupies 67.21 liters of volume. One more example. Volume of 880 grams of CO2 at STP. See, these are all the problems based on that 4 lines table just before we discussed. Method 1, now based on number of moles directly we can calculate. Based on weight also directly we can calculate based on weight. How? Here 1 mole is equal to 22.4 liters. In case of grams, weights, gram atomic weight is occupies 1 mole is equal to 1 mole. 1 mole is occupies 22.4 liters. So with respect to weight also we can do. So first method, moles with respect to number of moles. So N is equal to weight by gram molecular weight. Weight because here molecule is given, now CO2 is the molecule, it is a compound. So number of moles of CO2, weight by gram molecular weight, 880 by 44 is equal to 20 moles. Now 1 mole is contains 22.4 liter, but in the sample 880 grams is nothing but how many moles? 20 moles. 20 moles. So 880 grams is how much? 20 moles. So 1 mole, if 1 mole occupies 22.4 liters, 20 moles occupies how much? X and so X is equal to 22.4 into 20. 448 liters. That means if you take 880 grams of carbon dioxide, it is occupies 448 liters of volume at STP. Simple here. 88 grams of whatever the grams is there, first of all we need to convert in moles. Why? Because 1 mole occupies 22.4 liters now. If you find number of moles, 1 mole occupies 22.4, number of moles occupies how much? Y moles occupies X. Like that. And method 2, directly with the weight also we can do. Why? Because gram molecular weight of molecule occupies 22.4 liters. And 80 grams occupies how much? So gram molecular weight of molecule is how much here? 44 grams. 44 grams occupies 22.4 liters. 88 grams occupies how much? X. X is equal to 80 into 22.4 by 44. For 44 ones are 44 20s are. Then 20 into 22.4 gives rise to 448 liters. In any way we can do this if we know that table. Now next heading, percentage composition of different elements in a molecule of the compound. So generally this percentage composition is helpful to find out what amount of each and every element present in a molecule of the compound. What amount of each and every element is present within a molecule of the particular compound. That is called percentage composition of different elements present in a molecule of the compound. With the help of this percentage composition, we can write the empirical formula of the compound. That is why before writing empirical formula, we are discussing about the percentage composition of element within a molecule. So for that formula is there to find out each and every element percentage composition within a molecule. The formula is percentage composition of element is equal to number of atoms of that element into atomic weight by molecular weight into 100. Percentage now we need to multiply with the 100. So here percentage composition of element is equal to number of atoms of that element. That element means whose percentage composition you are going to find out. That element, number of atoms of that particular element you need to consider here into atomic weight of that particular element by molecular weight of that molecule into 100. Okay, example. If we see the example, we get it. So percentage composition of carbon in CH4. In CH4 two elements are there, hydrogen and carbon. So what amount of carbon is there and what amount of hydrogen is there? We need to find out that. For carbon we are finding the percentage composition. So percentage composition of carbon in CH4 molecule is equal to number of atoms of that element whose percentage composition we are finding here. For carbon we are finding, so therefore number of atoms of carbon we need to take here. So how many carbons are there? 1. So 1 into atomic weight of that element. Atomic weight of carbon is 12, so 1 into 12 by total molecular weight is 16. Sum of the atomic weights within a molecule is gives rise to molecular weight. So carbon 12, each hydrogen 1 means 4 hydrogens are there. 12 plus 4, 16. So 1 into 12 by 16 into 100 gives rise to 0.75 into 100 is equal to 75%. That means in CH4 molecule, in methane molecule, the percentage composition of carbon is 75. Okay. So in this way, we can find out the percentage composition of each and every element within a molecule. Now, if you want to find out the percentage composition of hydrogens within a same molecule, here percentage composition of hydrogen is equal to here. Percentage composition of hydrogen is equal to, instead of 1 here, how many hydrogen atoms are there? 4. 4 into here. What is the weight of atomic weight of hydrogen? 1. 4 into 1 by 16. 4 by 16. 4 by 16 into 100. 4 by 16 means 1 by 4. 1 by 4 into 100. 25%. So what is the percentage composition of hydrogen within a CH4? 25%. Remaining percentage is 75, that is nothing but carbon. In that way, we find out the percentage composition of each and every element within a molecule. And empirical formula. We know empirical formula. Empirical formula means, if you take the molecular formula means the number of atoms of each element present in a molecule, that is represented by the symbols and using subscript number, that is molecular formula. By using the simplest whole number ratios of each and every element present within a molecule, that is nothing but empirical formula. That means simple. The simplest whole number ratio of atoms of each and every element present within a molecule, it is giving rise to empirical formula. So it is the chemical formula of a compound which expresses the simplest whole number ratio of atoms of various elements present in one molecule of the compound, that is empirical formula. Simply we can say the simplest whole number ratio of molecular formula gives rise to empirical formula. Examples: glucose, name of the compound, molecular formula, empirical formula. We come to the glucose. Glucose molecular formula C6H12O6. Simplest whole number ratios. See here, 6 ones are, 6 twos are, 6 ones are. So 6 ones are, 6 twos are, 6 ones are. What we are getting? 1 carbon, CH1, H2O1, CH2O. This is the simplest whole number ratio of the glucose. That is nothing but empirical formula. So empirical formula of C6H12O6 is CH2O. Similarly, benzene C6H6. The simplest whole number ratio is what? 6 ones are, 6 ones are. C1H1, nothing but CH. So empirical formula of benzene is CH. Methane CH4. The least possible simplest whole number ratio is how much? C1s are 1, C1 4, 1, H4, CH4. Nylon 6, C12, H22, N2O2. Simplest whole number ratio, we is what? 2. 2 ones are, 2 6 are, 2 12s are, 2 11s are, 2 ones are, 2 ones are. So therefore C6H11, N1O1, C6H11NO. This is what empirical formula of nylon. Similarly, water, H2O, as a simplest whole number ratio of H2O is what? H2O only. Ethene, C2H4, 2 ones are, 2 twos are. So therefore CH2. Empirical formula of C2H4 is CH2. This is what empirical formula. And writing the empirical formula. So while writing the empirical formula, we need to know little knowledge about percentage composition of element, just now we discussed, and atomic weight. Atomic weight already we know that. So by using these two factors, we are finding the empirical formula of the compound. See, in the way we are writing empirical formula, that steps are given in the form of flowchart. First, mass of the atoms, mass of A atoms, mass of X atoms. Within a molecule, two types of atoms are there. A atoms, A element atoms, B X element atoms. So that is why we need to take the mass of A atoms, mass of X atoms. Okay. How we are getting that? With the help of mass percentages, nothing but percentage composition. For example, within a molecule, percentage composition of A element we are getting 75%. So mass of that A atoms is how much? 75. Mass of X atoms you are getting 25%. Mass of that one is how much? Mass percentage 75%. 25% means mass is 25. In that way we are finding the masses. After then, that mass is divided with the molar mass. Divided by the molar mass. It gives rise to number of moles. Number of moles. The number of moles is again divided with the simplest number ratios. Simplest number ratios means I will explain with the example table, then you understand that. See here, the most common form of nylon 6 contains 63.68% of carbon, 9.80% of hydrogen, 12.38% of nitrogen, and 14.4% 14% of oxygen. If the molecular mass of nylon 6 is 226, calculate the empirical formula for nylon 6. See here. Just now we discussed percentage composition gives rise to mass of that particular element. Okay, total mass of that particular element within a molecule we are getting from percentage composition. See here, in nylon 6 molecule, these are the elements present: carbon, hydrogen, nitrogen, and oxygen. In the within a problem, percentage composition is given. How much percentage composition? 63.68. Hydrogen 9.80, nitrogen 12.38, oxygen 14.14. Just now I said percentage composition of each element gives rise to its mass. So 63.68 means its mass, total mass of that element in that molecule is almost 63.68. Okay, and 9.80 means 9.80, 12.38, 12.38. So percentage composition giving rise to total mass. Now atomic masses, we know the elements atomic masses. Carbon is 12, hydrogen 1, nitrogen 14, oxygen 16. Then we are getting the simplest atomic ratio. The simplest atomic ratio is nothing but simplest, not simplest, the fourth column, atomic ratio. Atomic ratio is giving rise to number of moles. Why? Because here what we are considering, mass by atomic weight of the sample by weight of the substance by atomic weight of the substance by atomic weight is giving rise to what? Number of moles. So here atomic ratio is nothing but number of moles. So 63.68 by 12 is nothing but 5.30. That is what number of moles of carbon is how much in a given sample of that nylon 6, 5.30. And 9.8 by 1, 9.80. And 12.38 by 14. 0.88. So atomic ratio is simple. The total mass by atomic weight gives rise to atomic ratio. That is nothing but number of moles formula we are using. So in this way we are getting the atomic ratio values. In these atomic ratios values, if you observe the atomic ratios values, among these atomic ratios values, you need to pick up simplest atomic ratio value. 0.88 we obtained for nitrogen and oxygen. Any one of the value you need to take. Least simplest atomic ratio value is 0.88. Again this 0.88, that simplest value, again we are dividing with the number of moles. Number of moles means atomic ratio getting for each and every element. For carbon how much we got? 5.30. Among this least ratio is 0.88. So 5.30 by 0.88 gives rise to what? 6. Again 9.8 number of moles here obtained, atomic ratio here obtained 9.80 by 0.88, 11. 0.88 by 0.88, 1. 0.88 by 0.88, 1. Now we are obtained the simplest atomic ratio. Simplest atomic ratio. Then these numbers are we are giving to the atoms of an elements given in the first column as a subscript numbers. So then if you are writing this simplest atomic ratio of carbon 6 as a subscript number to the carbon C, what we are getting? C6. And 11 writing as a subscript number to the hydrogen, we are getting H11. For the nitrogen 1, for oxygen 1. So C6, H11, N1, O1. See here. So what is the empirical formula of nylon 6? Nylon 6, C6, H11, NO. Simple here. First of all, we need to Write the atomic masses with the help masses of the substances with the help of percentage compositions. If we don't know the masses of composition, a formula is there. Number of atoms into atomic weight by total molecular weight into 100. We are getting the percentage composition. Percentage composition we are expressing in grams, that is gives rise to mass. That mass is divided by the atomic weights, that is gives rise to what? Molar mass, nothing but atomic ratios. That atomic ratios we are considering the least ratio. That least ratio value is again that whatever the atomic ratios we are obtained, that ratios again dividing with the least ratio values, it is giving rise to what? Simplest atomic ratios. That simplest atomic ratio numbers whatever we are getting, that numbers we are keeping as a subscript number to as a subscript numbers to each and every element, that is giving rise to empirical formula. For example, nylon 6 we are obtained just now. So empirical formula mass we need to find out now. Empirical formula obtained. Now empirical formula mass. 12 carbons, how many are there? 6. So 6 into 12. How many hydrogens are there? 11. 11 into 1 plus how many nitrogens are there? 1. 1 into 14 plus 1 into 16. So total how much? 113 unified masses, means 113 grams. So empirical formula mass of nylon 6 is how much? 113 unified masses, 113 grams. Now number of moles. Number of moles formula is what? N is equal to molar mass by empirical formula mass. N is also considered as what? Here integer. So molar mass by empirical formula mass. Molar mass of the nylon 66 is how much? 226 in the problem is given. 226. 226 by empirical formula mass just now we got 113. So 226 by 113 is gives rise to what? 2. So N is nothing but 2. So molecular formula of the compound we are writing with the help of this N value and empirical formula. So molecular formula of a compound is equal to N into empirical formula. N value how much we got? 2. So 2 into empirical formula just now you got C6H11 N1 O1. So N nothing but NO. So 2 into C6H11 NO. 2 6 the 12 C12. 2 11 the H22. 2 into nitrogen, 2 nitrogens, N2. 2 into oxygen, 2 oxygens. So C12H22 N2 O2. This is the molecular formula of nylon 6 molecule. So this is the atoms and molecules chapter, the important topics of atoms and molecules chapter. Mostly maximum we discussed.